Hi, my name is Gleb Posobin, and today I'm going to tell you about our paper called Data Structure Lower Bounds in the Group Model. First, an example of a static data structure problem. You're giving a graph of United States roads between cities, and you're asked to process the roads in such a way that when you get a pair of cities, you're able to efficiently respond with the distance between them, the shortest distance between the two cities. And the preprocessing stage can take as much time as you want, but the limitation is in the query stage. You're allowed to read only at most T memory cells that you've pre-computed. And the allowed space to use is S. And of course, the goal is to minimize the total space used and the query time T. So this is an example of static data structure problem. Another often encountered such problem examples are nearest neighbors problems, where you're asked to preprocess a set of points in some metric space so that you can efficiently find closest points to a given query point. Another kind of problems is range counting problem, is where you're asked to preprocess the points in some space so that you can efficiently compute afterwards the number of points in a given region. And region can be a rectangle, it can be polygons, it can be half spaces or something like that. So what is the definition of the static data structure? First part of the definition is there are n inputs to the data structure. This can be points or it can be vertices of a graph. And you need to preprocess them somehow into S memory cells. Each memory cell can be a group element of a group, it can be a bit string. In our case, it will be elements of a group ZP. And the processing time is unbounded. All the computations on this stage are allowed to be whichever you want, and you can take as much time as you want to create those S memory cells. And then afterwards, you're supposed to be able to respond to the M possible queries. And to respond to each query, you're allowed to read only at most T memory cells, either in adaptive or non-adaptive fashion. There are two possibilities. Usually M in our problems is polynomial in N. So for example, for the shortest distance problem, it would be about N squared, and the space is ideally linear in N. We say that data structure is efficient if the space used is linear and the query time T is at most polylogarithmic in N. So of course, there are always two trivial solutions to any static data structure problems. First solution is you just pre-compute all the answers when you get the queries. Then each query takes only one memory probe to answer. It takes only one memory cell, but the memory used is M, the number of possible queries, which is not ideal. And the other possibility is that the space is very good. You just store all the input points that you were given. But to answer queries, you just do the calculations on those query points. Potentially all of them are new. So you have to go through all the input points. And so the query time in this case is very bad. So there exist problems that require the space to be approximately M or time to be approximately N. And this can be shown easily by counting arguments. And yet the best known lower bound is as follows, which first has the following form. And for the case of T linear in N, it gives only logarithmic lower bound. And for space even slightly superlinear in N, it's the lower bound is trivial. So this is a cell probe lower bound. This is a cell probe model, and as I said, there we allow arbitrary functions to be used on the query phase. We are not limiting in any way the function used to compute the query result from memory cells. There are more restrictive models, such as linear model, where we allow the query result to be a linear function of the memory cells. Again, each query can to answer each query, only T memory cells can be accessed, but the function now is required to be a linear function of those inputs. And it has been recently shown that improvements on logarithmic lower bounds in this model would lead to new circuit lower bounds. So it is also probably a hard problem. And so even more restricted version of that is where we allow only additions and subtractions of the memory cells. And in this model is called group model. Again, the best known lower bound here was log n, and our work improves on that. And the most restrictive version of them all is the semi-group model, where we only allow addition of the memory cells to compute the queries. Optimal lower bounds were known then for 20 or 30 years. So we improve in the group model, as I said, and we give an explicit problem with the cubic number of queries such that any structure in the group model with linear space must have a polynomial query time. So this kind of separates this group and semi-group models from the harder linear and cell probe models. So in the group model, the problem we're working with is the range counting with weights. The input points, as in usual, there are input points as in standard range counting, but now they have weights. Here they're integers, or generally for our case, they come from ZP, cyclic group modulo P, and the possible queries are some rectangles or triangles, and for us, it will be just polygons with many sides, potentially. So if such a query comes as a triangle, the data structure should be able to respond with 8, the sum of the numbers inside the triangle. And when such rectangle comes, the sum of the numbers inside is 9, and so data structure should be able to respond with 9. So how our proof goes of the aforementioned theorem. First, we show that efficient data structures, their outputs are not diverse. That is a property I'll discuss later, but any output of any efficient data structure, we can show to be not diverse as soon as the group size is large enough. Then we show that if for the range counting problem, the incidence matrix has a certain property known as k-wise independence, then the outputs, when we assign random weights to the input points, the outputs with high probability will be diverse. And so such a range counting problem, if it has such an incidence matrix, it cannot be solved by an efficient data structure. Then we show that such k-wise independent matrices do exist. This is not trivial because the incidence matrix has to be a 0-1 matrix, and it was not obvious that such matrices do in fact exist. And we've shown that the random matrices are k-wise independent and random 0-1 matrices. Then we randomize this construction. Constructing a random matrix takes n m random bits, and we were able to decrease the number of bits required for that using Derandomization techniques. And then we embed this random matrix into a range counting problem in 2 dimensions where the ranges are polygons, convex polygons. So what is diversity? We call the set as diverse if for any residue modulo P, non-zero residue, when you choose any such residue and multiply all the elements of S by it, there we will be able to find such an element small s in S, such that Q times small s is large modulo P, that is just far from 0 modulo P. For example, the set of all residues modulo P is of course diverse. As an example of a smaller set that is also diverse is the set of all powers of 2, of first log P powers of 2. And if you think about it for a little while, you'll be able to see that for every multiplier, indeed, it is possible to find a power of 2 such that when you multiply q by power of 2, it will lie inside this interval from p over 4 to 3p over 4. So it is quite far away from 0 modulo p. And so the set S is diverse. Next step, so now the first step in the proof is showing that the outputs of efficient data structures are not diverse. The lemma can be stated as follows: if we have any data structure that uses query time t and its space is S, then if the group size p, we're working in a group ZP for prime p, and if p is greater than 4t to the power s, then the outputs of the data structure are not diverse. And that is a simple statement, and it has a simple proof. So how do we prove that? So we want to find some multiple such that such multiplier. We want to find a multiplier multiplying by which we will get. We will make all the outputs small. But we know something about our data structure. Namely, we know that we're working in a group model, and so any output is obtained as a sum of at most t memory cells. And there are only a few memory cells, namely there are only O of n memory cells. And so it should be easier to find such a multiple for the memory cells instead of the query outputs. And finding, so if we are able to find a multiple q such that q times p1 is at most p over 4t, q times p2 is p over 4t modulo p, and so on, taking a sum of at most t of such elements will give an element of absolute value modulo p at most p over 4 for any query. And so all the outputs of the data structure will be bounded by p over 4 modulo p. And this will give us this will give us the required proof of non-diversity. So now we need to ask, when can we find such a Q that all these memory cells can be made small by multiplying by Q? And there is a statement in number theory called Dirichlet simultaneous approximation lemma, and that says that there always exists such Q for p large enough, larger than 4t to the s. And the proof is pretty simple. You should be able to deduce it from those pictures. This is for the case of s equals 2, and it is a simple application of pigeonhole principle. So next, if so yes, we showed that for any data structure and any input, as long as the group size is large enough, then the outputs of the data structure are not diverse. And our parameters require us to choose the p being a super polynomial in p. It has to be like n to the n, basically, which is not a problem. The data structure is allowed to interact with the group. It's not doing the multiplications in the group itself. You can think of it as data structure making queries to the oracle and asking to multiply the given group elements from the group and so on. And so to find and it is unbounded. The computation is unbounded during the query time and the processing time. So the size of the group is not a problem here. And our goal now is to find a data structure problem such that has n inputs and n outputs, and that those outputs, when given some weights, will, and when we choose some weights for the inputs, input points, and when we choose some weights for the input points, the outputs on this problem will be diverse. That will mean that any no efficient data structure can solve this problem, static data structure problem. Unfortunately, the case of the previously mentioned set of powers of 2, it is diverse, but it's not. It can be shown that it's not an output of any range counting problem, so it doesn't help us. We want to have a range counting problem that gives a diverse set. So how do we obtain a diverse set? One property that allows this turns out to be k-wise independence, namely linear k-wise independence of the rows of the matrix. And let me go into more detail. If you have a range counting problem, it can be encoded. If you know the inputs, you can take the incidence matrix, which is 0, 1, and it has 1 in all the, it has rows corresponding to the shapes, rectangles or polygons. In our case, it will be polygons, and columns corresponding to points, and there is an 1 at that point in the matrix for those points which lie in the corresponding shape. So on the intersections of i's points and j's shape, there is a 1 if i's point lies in j's shape. And so all the outputs of the weighted range counting problem can be written as a multiplication of the matrix M, 0, 1 matrix, by the vector W of the weights assigned to the points. And the vector W, and the main idea is to choose the vector W uniformly at random. If M were a non-singular square matrix, then the output MW would be uniformly at random. And it is easy to show that such a uniformly random vector, as long as it is large enough, longer than log p, then with high probability this random vector would be diverse. But turns out but our matrix M is not square. It is it is a very long rectangle. It has, in our case, it will have n cubed rows and n columns. So this doesn't go through exactly, but there is a version of Chernoff bounds for k-wise independent variables that allows us to prove the same statement, that most of the outputs, if W is uniformly random, then most of the outputs would be diverse. We can show it using this version of Chernoff bounds. As long as M has the property of being k-wise independent, that is, any k rows of M are linearly independent. It says not immediately clear that such matrices M even exist, because M has to be an incidence matrix, so it has to be a 0, 1 matrix. It's not clear whether 0, 1 matrices that have k, and for us k needs to be about n. It has to be linear in n, say n over 100. So any n over 100 rows of this matrix of size n times n cubed have to be linearly independent, and all the rows are, all the elements are 0, 1. It's not clear that such matrix does in fact exist. So the next step is to show that such matrices do exist, and we show that the random matrix is in fact linearly k-wise independent. And just the trivial upper bound, trivial bound using union bound doesn't work. It doesn't help here because there are too many submatrices of such a large matrix, and the probability of each one being singular is too large, just 2 to the minus n. There are such matrices with such properties that are omega n-wise independent, and more exactly n-wise independent if you take M to be a van der Monde matrix over the reals. And also, if we relax the restriction of k, if we make it not linear but allow it to be n over log n wise independent, then it is enough to take M to be a parity check matrix of any good error correcting code over F2, and then it will be k-wise independent. But n over log n wise independence is not good for us. For us, we need linear n-wise or omega of n-wise independence to get our result. So we prove that a random matrix is omega n-wise independent, and also such matrices are known as compressed sensing matrices. because they allow to recover sparse vectors from a few observations, and it is the first separation of such compressed sensing matrices from matrices known in compressed sensing literature as RIP matrices, and the proof of these results goes through the Littlewood-Offord lemma, just using this basic anti-concentration inequality and over reals and also over the finite fields. So now we have shown that the random matrix is k-base independent, and the next step we want to do is randomize this construction. That is, we want to use less random bits than a random uniformly random 0-1 matrix needs. For that, we notice that our proof uses only the Littlewood-Offord inequality, and it has the following form, where xi's are real numbers or the elements of finite field, and epsilon i's are signs, uniformly random signs from the same column inside the matrix. And to keep the proof the same, but taking the randomness, but to use less randomness, to use a PRG instead of a uniformly random source, it is enough to keep this inequality basically the same, not improve or not increase the right side too much. And so we basically need to fool the hyperplanes, these equalities. So the probability of satisfying this equality that has to stay about the same under the PRG when we sample the columns of the matrix from the PRG and under the uniformly random signs. So there is a PRG that works against hyperplanes and originally against half spaces, and it uses O of log n with the tilde hiding log n squared factor. So now instead of generating random columns, we're independently generating every column, but from a PRG. And the total number of random bits used is now n log n instead of the previously used n to the fourth uniformly random bits. So now we can generate this matrix using fewer bits, that is, we sample from a smaller subset of matrices. And now we need to embed this problem into R2, make it into a range counting problem. We do the following trick to do this. Take the 2 to the R points where R is the seed length, and label them with outputs of the pseudo-random generator on that input. In this case, the length of the output of the pseudo-random generator is just 3. And now we have these points on the circle. Look at the first bits of all those pseudo-random generators outputs and connect the ones that have in the first bit set to 1. That would be your first polygon, our first polygon. And then look at the second bit and make a second polygon the same way. Look at the third bit, make the third polygon this way, and so on. Now we have a bunch of polygons. They have about 2 to the R sides, which is a bit too much. It is slightly. It's not linear, and it is not quite. It is not polynomial. R, I remind you, is log n times log n squared. But this is the best that we can achieve using this PRG. And if there's better PRG against half spaces, it will give an improvement to this result directly. So we have those polygons with many sides. Now our previous discussions show that there exists a set of endpoints on the circle. We don't know which ones, but they do exist, such that this outputs, those strings, when you write them into a matrix as a columns, this matrix will be k-wise independent for k equal n over 100. So we know that that implies that there exists a set of weights that we can assign to those points, such that the outputs of the data structure problem have to be diverse. So the sum of the points inside each polygon, if you compute those weights, and the outputs will be diverse with high probability if you assign the random weights to those points. And so there is a data structure that's data structure problem that's does not admit an efficient a solution by an efficient data structure. So that is the result. And thank you for listening about our paper.